Okay, so recursion is an alternate way to implement iteration, which means another way to implement repetition or looping in your program. And it's implemented by a function that calls itself. It's important, the most important thing for you to know is that you either use a loop or you use recursion. So you should never have a recursive function that has a loop inside of it. So inside of any recursive function, you should not have while, do while, or for. Recursion replaces loops. Okay, so the idea with recursion is that one of the subtasks to be solved is nothing more than a simpler version of the same program. So a classic example to look at with recursion is the example of factorial from mathematics. So 5 factorial is just 5 times 4 times 3 times 2 times 1 times 1. And it's really just the same as 5 times 4 factorial. So nothing more than a simpler version of the same problem. So 5 times, then 4 factorial is a simpler version of the same problem. The base case, or the stopping case, is when you reach 0 factorial, which is 1. And the general case, or the recursive call, for n factorial is n times n minus 1 factorial. Now, it's also important to note, if you don't have a base case or a stopping case, you will get an infinite loop with recursion, okay? A factorial example could be done with just regular iteration, okay? You could have, n, if we pass this in for n factorial, like 5 factorial, this variable factorial is 1, and we just have a loop that counts down, and every time through it multiplies, whatever you started with, your 1 times equals n. So like the first time, if this was 3 factorial, I would be 3, fact would be 1 times 3, which is 3, and next time it would be 2, and this would be 3 times 2, which is 6, and etc., etc. So this is an example that can be done with a for loop, but it can also be done with recursion. So here we're going to look at the recursive solution. Okay. And the prototype is the same, the return type is the same, right? It just still passes in n. And this shows you your general case. If n is equal to 0, we return 1, else we return n times recursive factorial n minus 1. So let's look at this example. Let's say somebody calls the function and they try to figure out 3 factorial. So, it just says cout, 3 factorial is, and here's the function call. So we pass a 3 into this function, and it always looks the same. If n is equal to 1, right, it's not, it's a 3, else return 3. Now remember, you're returning n, which is 3, times n minus 1, which is 2. So what's happening right here, right, is this is now jumping out to its own recursive call. This recursion is not finished yet. This is a function call. It jumps out to this function call. So now we pass 2. Is n equal to 0? No, it's not. So we return n, which is 2, times, and we call it again with n minus 1. So 2 minus 1 is 1. So again, this jumps out and starts executing this function right here. Okay? So now this time through n is 1. Is it 0? No. So we're going to return 1, which is n, times, we're going to call a recursive function with 1 minus 1, which is 0. And then we call this function again. This time with 0. Is n equal to 0? Yes. So it returns 1. So let me explain what happens when this returns. So this returns a 1, and it returns it right to here, the 1. Now this function's going to finish 1 times 1, right? 1 times 1 is 1, and it returns it right back to here. That's where it got called. So it returns the 1 time back here, and now we've got 2 times 1 is 2, and this function returns it right back to here, and this is 2. And now this function is done. It returns 3 times 2, which is 6, and it returns it right back to here. And so what's going to display here is 3 factorial is 6. Now, if you think about how that happens, you could have a lot of overhead in recursive solutions, because I just had a main program probably that had this in it. When this gets executed, it pushes this on the runtime stack and it jumps out to this function. And when it hits this recursive call, it pushes everything about this function onto the runtime stack. Things like local variables, the address, where the function's located, when it returns, etc., etc. And then it comes out to here. And then when this happens, it pushes all this stuff on the runtime stack. And then it comes out to here, pushes all the information about this function on the runtime stack when it comes out to here. And when it does return back, it then pops everything off about this function. And then this returns to get back here, it pops all this off, right? And then it comes back to here. So these things that are getting pushed on the runtime stack are, sometimes they're called activation records. It's just a structure, could be a class object that contains all the information about the function. So you can see what that would do if we do recursive factorial 3. If you did recursive factorial 33, you would have 33 of these things pushed onto the runtime stack. If you did 330, you would have 330 of them in, and this is probably not an efficient solution. So this particular type of recursion that you see in this example is what's called tail recursion, where the recursive call is kind of at the end. And a lot of times when you have tail recursion, it kind of tells you that, this might be better done in a for loop. So this particular example we use because it's relatively easy to understand, but overall maybe not a great recursive function, right? Factorial might be better written this way. So in the next example, we'll see something that's a recursive solution, but it would be more, it's a solution where a recursive solution is more efficient.